Hello everyone. I think you are exploring the concept of alcohols, phenols and ethers. Have you noticed that alcohols having OH functional group can behave as nucleophiles as well as electrophiles? They behave as nucleophiles because the oxygen atom has lone pair above it. And we know that nucleophiles are lone pair holders or maybe negatively charged as well. So alcohols can act as nucleophile. Alcohols can also act as electrophiles when they get protonated because the lone pair above oxygen is capable of abstracting proton and forming protonated alcohol, which is also termed as oxonium ion. This oxonium ion has a positive charge over oxygen atom, which is electronegative. So obviously it induces a polarity in the adjacent carbon-oxygen bond, giving delta positive character to the carbon which is directly bonded to the oxygen. So have you thought of all these things? If not, then it's time to think about it. And alcohols have OH functional group. They show reactions due to the breaking of the oxygen-hydrogen bond, and they show reactions due to the breaking of carbon-oxygen bond as well. So let us discover reactions of alcohols, reactions of phenols involving oxygen-hydrogen bond breaking and carbon-oxygen bond breaking. So let's explore. Now here there are two reactions that we can see of alcohols. The first one where there is a carbocation over here, and the second one where there is a proton over here. So what do you think will be the role of alcohol in these two reactions? In the first one, the oxygen has lone pair, and so don't you think the alcohol is acting as a nucleophile here? And this is your electrophilic center, and the lone pair over oxygen attacks the electrophilic center, the carbocation. And what you get over here is our oxygen is having the hydrogen, and it has already attacked using one lone pair, so there is a positive charge over oxygen, one lone pair remaining, and it has bonded with the carbon which was having the positive charge. So this is what you have obtained. Now in the second reaction, you are seeing another alcohol, and I have given you an example of 1 degree alcohol plus H plus. What can happen over here? Same thing can happen over here. The lone pair above oxygen will abstract the proton. And now what are you supposed to get? You will be getting R CH2, and the lone pair is used up. So a positive charge above oxygen. One lone pair will be remaining. It had one H. Another H is abstracted and one lone pair is remaining. Now don't you think that this electronegative oxygen atom will actually want to get rid of that positive charge? So if in the medium there is any nucleophile, say X minus is a nucleophile, Br minus I can consider over here. So if there is any nucleophile in the medium, it will attack the electrophilic site, and please don't think that it will attack the oxygen side. It will attack the carbon end because the carbon end attains electrophilicity on account of the greater electronegativity of oxygen atom which has attained a positive charge. So this positive charge above oxygen atom induces a polarity in the carbon-oxygen bond, and for which the carbon end attains a delta positive nature. This carbon attains a delta positive nature. That's why it attacks to this carbon, and OH2, I mean water molecule, goes out as a neutral leaving group. H2O is a neutral leaving group, and it's a very good leaving group. So you have seen the nucleophilicity of alcohols. You have seen protonated alcohol. This was your protonated alcohol, which is known as oxonium ion. I told you that protonated alcohol is known as oxonium ion. So the oxonium ion actually generates this end, which is electrophilic in nature, and a nucleophile can attack that carbon. So next we can move on to reactions involving oxygen to hydrogen bond breaking. So this bond breaking, when I talk about, then obviously I talk about release of H plus. When this bond breaks, it releases H plus, and when it releases H plus, it talks about acidic nature of alcohols and phenols because it releases H plus. Now, can you give evidences to this reaction? Can you say that it actually gives H plus, and in presence of active metals like sodium, it readily releases this H2 gas? It produces H2 gas? Yes, of course. ROH reacts with active metal like sodium and it releases H2 gas, forming RONA. RONA is known as sodium alkoxide. It's known as sodium alkoxide, and it releases hydrogen gas, H2 gas. So this reaction with active metal, if you balance it, it is 2 over here, 2 and 2. So it reacts with active metal sodium, forming hydrogen gas. Phenol also reacts with active metal sodium, so forming sodium phenoxide. So this is phenol. 2 moles of phenol reacts with 2 moles of sodium, forming sodium phenoxide. So this is ONA, C6H5ONA is known as sodium phenoxide. And if you can test the presence of the H2 gas, you can say that this is an evidence for the reaction and evidence for the acidic nature of alcohols and phenols, if you can test for the presence of the H2 gas. Phenol also reacts with base. Like any acid-base reaction, phenol reacts with base NaOH, forming sodium phenoxide again, and water. In the previous case with active metal, you have seen formation of sodium phenoxide and hydrogen gas. Here you are seeing the formation of sodium phenoxide and water, just like any other acid-base reaction. These are the two reactions. Now, the above reactions are showing that alcohols and phenols are acidic in nature. See, alcohols and phenols are, we can say they are Bronsted acid as well. They are Bronsted acids as well. Why? Because they can donate H plus. They can donate proton. So if I say ROH, alcohol, this is the oxygen with its lone pair. Now, if there is a base in the medium, suppose there is a base in the medium, the base can abstract the H plus and it can form alkoxide ion. Okay, so we can say that the base is abstracting the proton and it forms BH. If it abstracts with the lone pair, then BH plus. And this actually is your conjugate acid because it is capable of donating the H plus, and it forms RO minus, which is your conjugate base. So in that case, we are seeing that this alcohol is acting as an acid. But the acidic nature of alcohols are very, very weak. It is acidic, we will say, to some extent because of the polar nature of the OH bond. An electron releasing group, like any R group, this R group, it can be methyl, it can be ethyl, any other alkyl group. It increases the electron density over the oxygen due to its plus I effect. Now that decreases the polarity over oxygen-hydrogen bond. I said that ROH, this oxygen-hydrogen bond, has polarity due to the electronegativity difference. But this R group which is attached, suppose I say RCH2OH, a more specific example of a 1 degree alcohol. This is a 1 degree alcohol. I say R2CHOH. This is 2 degree alcohol. R3COH. This is 3 degree alcohol. Now when the number of alkyl groups are increasing, the inductive effect is also increasing. Plus I effect is also increasing. Now this plus I effect actually increases the electron density over the oxygen atom, for which the OH bond polarity decreases. The OH bond polarity decreases. So I will say the acidic nature, when I move from 1 degree to 2 degree to 3 degree, it gradually decreases. It gradually decreases. This is your acidic nature of the alcohols. Gradually decreases. Why? Because the R group present, the alkyl group present, it has more the number of alkyl group having plus I effect. It increases the electron density over the oxygen atom and hence decreases the polarity over oxygen-hydrogen bond. Now ROH, alcohols, are even weaker acids than this water. You know that you can illustrate this by the reaction like say alkoxide ion, RO minus. It acts as a base. Why you know? It is capable of abstracting proton even from water. So water has amphoteric behavior, we all know. RO minus, it abstracts the proton from water and forms OH minus. So what we are seeing over here is RO minus takes the proton and forms ROH. Now this is a conjugate acid and OH minus is formed and this is a conjugate base. So we can see that water is a better proton donor. And so we can say that H2O has greater acidity than ROH. This is the acidic order. So for that reason, when you will do the practicals related to organic functional group in your class 12 or maybe you have done, there you have realized that to litmus action, alcohols are considered to be neutral. Why? Because its acidic nature is so less, it is so weak that even water can be considered to be a better proton donor than the alcohols. Now talking about phenols. Phenols are highly corrosive. So carbolic acid is corrosive in nature. And this is the structure of phenol. This oxygen-hydrogen bond is highly polar. Why? because the lone pair above oxygen goes into resonance, and due to this plus R effect, the oxygen hydrogen bond polarity increases. Whenever the electron density moves away from the oxygen atom, then only oxygen hydrogen bond polarity increases. And we can see over here the electron density moves away from the oxygen atom and goes to the benzene ring, for which we can say that the plus R effect, on account of the plus R effect, the oxygen hydrogen bond polarity has increased. So for which we will see what is happening over here. There develops a negative charge, and after this what happens is, due to the plus R effect, the lone pair comes and forms a double bond between oxygen and carbon. This hydrogen is as it is. The lone pair is used, so one lone pair remains and oxygen gets a positive charge. And here we are seeing these bonds are unaffected. This pi bond has come and formed a negative charge over here. Now, this negative charge which you have got, this negative charge is in conjugation with the pi cloud, and you will be getting other resonating forms like this. This negative charge forms a double bond opens up and forms a negative charge. So again you will get resonating forms. These are the resonating forms. So we can write like this. How to form the resonating form? See, this part is unchanged. Nothing has happened to this. So write the part which is unchanged first. This is the unchanged part. And here this is also unchanged part. The negative charge comes and forms a double bond. Double bond opens and forms a negative charge. Next, what will happen? Try and move the arrow either in clockwise or in anti-clockwise. Don't move in both the directions. Again, the negative charge will come and form a pi bond. Pi bond will open and form a negative charge. So, again you will get this type of resonating form. So, I said whichever is unchanged, first draw that. Unchanged. This part is unchanged. Lone pair remaining, positive charge. Now the change. Negative charge forms double bond forms negative charge. The last one will be this coming and forming a double bond, and this opening and neutralizing the charge over oxygen. So let us see what is happening over here. Whichever is unchanged, draw that first. Now the change. Just a minute. Double bond, and the double bond opens up, and OH, oxygen getting back the lone pair. So these are the resonating forms, and that is what I have explained, the plus R effect. Now this plus R effect of phenol creates oxygen hydrogen bond polarity. It develops oxygen hydrogen bond polarity, for which H plus can be readily given to a base. Once this H plus is given to a base, what happens is it forms a phenoxide ion. Now this phenoxide ion which is formed, the conjugate base after H plus is given by phenol, this is your phenoxide ion, and this phenoxide ion is a conjugate base, and this is again resonance stabilized. So this conjugate base is resonance stabilized, and whenever a conjugate base is stabilized, we will say the compound phenol is having considerable acidic nature. And another factor, not only plus R effect, another factor due to which we can say that the oxygen hydrogen bond polarity is more is the sp2 character. That means sp2 hybridization, greater S character of this carbon atom, which actually has greater electronegativity. So obviously it will pull electron towards itself in this oxygen and carbon bond, for which again a polarity develops in this oxygen and hydrogen. So two things you have to say when you are comparing acidic behavior of any compound. I mean alcohol, phenol, substituted. You talk about first OH bond polarity. If the bond polarity is greater, then the acidity is also greater. Then only H plus can be released easily. Talk about conjugate base stability. If the conjugate base is stable, then the compound is more acidic in nature. Like in phenoxide ion, we talked about OH bond polarity due to the plus R effect, due to the greater S character of the carbon atom, which is sp2 hybridized, which is directly attached to oxygen. And we told about the stability of the conjugate base, the phenoxide ion, resonance stabilized, and so it is acidic in nature. Now we will be talking about substituted phenols. We will be talking about substituted phenols. What is substituted phenol? In substituted phenols, suppose I have a phenol structure I am telling. I am comparing this with another substituted phenol where I am having an electron withdrawing group like nitro. Okay, so I can also compare it with substituted phenol which has an electron donating group like alkyl group. Now anything that withdraws electron from the ring, electron withdrawing group, it withdraws electron from the ring means this increases the oxygen hydrogen bond polarity because it withdraws electron from the ring, so withdraws electron from oxygen. And for the same reason, see, if I say the conjugate base, then the conjugate base of this phenoxide ion, O minus after giving out the proton, in presence of electron withdrawing group, it actually produces better negative charge delocalization. Better negative charge delocalization. Delocalization means flowing out. Due to the electron withdrawing effect of the electron withdrawing group, the negative charge goes towards the electron withdrawing group, and that is known as delocalization, flowing out of the charge. Delocalization is stabilization and charge concentration is destabilization. अगर कोई फैक्टर से ये नेगेटिव चार्ज अबव ऑक्सीजन कम हो जाता है तो ये स्टेबलाइजिंग फैक्टर है, तो ये डीलोकलाइजेशन है. इलेक्ट्रॉन विथड्रॉइंग ग्रुप अपने तरफ इलेक्ट्रॉन को खींच लेगा जिसके कारण ये नेगेटिव चार्ज डेंसिटी जो है ऑक्सीजन के ऊपर कम हो जाएगा, एंड दिस इज अ स्टेबलाइजिंग फैक्टर. सो one stabilizing factor is the bond polarity between oxygen hydrogen due to the presence of the electron withdrawing group. The next stabilizing factor is the negative charge delocalization of the conjugate base. But in case of electron donating group, since it will donate electron, it will decrease the OH bond polarity, and for the same reason it will decrease the stability of the conjugate base. So obviously if I say I am going to arrange them in decreasing order or increasing order of acidity, I will say most acidic will be the substituted phenol containing electron withdrawing group. Then will be phenol, and then will be the phenol, substituted phenol having electron donating group. because it decreases oxygen hydrogen bond polarity and decreases the stability of the conjugate base. Now, if the number of electron withdrawing group increases, then the acidic nature also increases due to greater OH bond polarity, and stability of conjugate base. So this part is very, very important. So please note that this is the nature, this is the order of acidic behavior of phenols and substituted phenols. And if the number of electron withdrawing group increases, then what happens? The acidic nature also increases. After this, we have the esterification reaction or ester formation reaction. In esterification reaction, do we know what is ester linkage? This linkage is known as ester linkage. And there are three reactions. First one is AROH, or I will say ROH, reacts with carboxylic acid, R dash C double bonded O OH. It reacts with carboxylic acid in presence of acid as catalyst to give you ester. So this is the ester plus H2O. So it is esterification reaction. This esterification reaction can be used to test, or rather to confirm, the presence of alcoholic OH group and carboxylic acid group in your practicals. This test is known as esterification test. Now, ester formation doesn't take place only by acid. It takes place by acid anhydride as well. AR or ROH, it reacts with anhydride of acid. C. It reacts with R dash C double bonded O. Okay, so O C double bonded O R dash. Anhydride of an acid is obtained by the removal of 1 mole of H2O from 2 moles of the acid. So you will get, in presence of H plus, you are going to get AR or ROC double bonded O R dash, which is again an ester, and R dash COOH. This is acid. Next we have another way of preparing ester with acyl chloride. This, acid chloride. So alcohols, phenols, in presence of R dash COCl and pyridine. Pyridine is an organic base and it forms R or AROCOR dash plus HCl. Now do remember that this organic base pyridine helps in the removal of HCl to give a better yield of the ester. And these are the three reactions by which you can obtain ester. Do you know that aspirin has medicinal character? Aspirin is a drug which is now banned, but it was rather used as an analgesic. Analgesic means painkillers. It was used as an analgesic, painkillers. It is also used as antipyretics. Antipyretics means reduces fever, and also it prevents heart attack. You know how? By preventing clots. It prevents clots. So aspirin has medicinal aspects. Aspirin has medicinal aspects, and this aspirin is also known as, it has IUPAC name, it is known as acetyl salicylic acid. It is known as acetyl salicylic acid. How can you obtain aspirin from phenol? You actually have to obtain salicylic acid from phenol, and then you have to obtain aspirin from phenol. So, let us see how to do so. Phenol actually undergoes a name reaction which is known as Kolbe's reaction, and also another reaction, Reimer-Tiemann. We will discuss about this in the later phase. So first I will say giving NaOH, second I will say giving CO2, and third I will say giving H+. It forms salicylic acid. It forms salicylic acid. Now remember that Reimer-Tiemann can give you salicylaldehyde also, salicylic acid also. So this, what is the name? The name is salicylic acid. You can see it is 2-hydroxybenzoic acid. What is the IUPAC name? 2-hydroxybenzoic acid is salicylic acid, 2-hydroxybenzoic acid. Now you can carry out esterification the way we have seen how the OH group reacts with anhydrides we have seen. So acetic anhydride, I can say CH3CO whole twice O is acetic anhydride. In presence of H+, it will actually give acetyl group. And what is this acetyl group? C double bonded O CH3. This is acetyl group. Now this H of phenol is substituted by this acetyl group, and you get over here in place of H O C double bonded O CH3. The acetyl group comes, and COOH remains as it is, plus acetic acid CH3COOH. The one which you have obtained is known as aspirin, and it is acetyl salicylic acid. Why? Because acetyl substituted. So it is acetyl salicylic acid. So this is how you can obtain aspirin from phenol, by the method of obtaining salicylic acid. So this reaction is known as Kolbe's reaction, not the entire reaction, only Kolbe's reaction is this much. So after Kolbe's reaction, this reaction is known as esterification reaction. So first is Kolbe and then is esterification in order to obtain aspirin. Let us see the dehydration of alcohol with ethanol as the example. In ethanol, we can see that there is, we can see that the lone pair above oxygen, it is, just a minute, the lone pair above oxygen, it is abstracting the proton, this is abstracting the proton, and it forms oxonium ion, protonated alcohol, oxonium ion. Oxygen is electronegative, it gets a positive charge. So my slow step, rate determining step, is the second step, because there is formation of a carbocation, and here only a 3-degree carbocation will be more stable than 2-degree, will be more stable than 1-degree. So for the alcohols, the reaction rate also follows the same order. Now here we can see that the oxygen wants to become neutral, and so it takes electron from the carbon-oxygen bond. Now you get a carbocation. Now there is finally elimination. See, here there is water molecule. You know water has amphoteric behavior. So this H2O, the oxygen has lone pair, and with this lone pair it abstracts this proton. Okay? Or if you say that we want to show the way it is shown in the book, then you show this proton abstraction. There is a formation of double bond here. So now there were three hydrogen over here. This is abstracted, and so you are left with 2 hydrogen. So CH2, there is a double bond, and CH2, and actually you have, in place of this H plus, you actually have H3O plus. Why? Because H2O is taking the proton. So first step 1 is protonation. So step 1 is protonation. Step 2 is dehydration, because there is removal of H2O. Dehydration and formation of carbocation intermediate, and it is your slow RDS, rate determining step. Since the stability of the carbocation will be 3 degree greater than 2 degree greater than 1 degree, the same follows the rate for the alcohol towards the reactivity. And finally, the proton is abstracted by H2O, formation of a double bond, and you get. Now we'll discuss about oxidation reaction for alcohols. Oxidation can be known as removal of H2 as well, so dehydrogenation. After removing H, this bond and this bond breaks, and you get a carbonyl compound plus H2. So oxidation is also known as dehydrogenation, removal of hydrogen. And we have seen one simple thing, that 1 degree alcohol, or we can say RCH2OH, that undergoes oxidation to form aldehyde, and aldehyde undergoes further oxidation to form carboxylic acid. And if I give a very strong oxidizing agent, that means 1 degree alcohol on strong oxidation can directly go to carboxylic acid. These strong oxidizing agents can be acidified. KMnO4, KMnO4H plus I can write. That can convert it to acid directly. Now, or it can be CrO3 is also an oxidizing agent. But you know what? CrO3 can restrict the reaction till aldehyde. A better oxidation can be carried out in a controlled manner. That means, suppose, I want to control the reaction, control the oxidation. I want to restrict the oxidation till aldehyde. I don't want to get the acid. I want one step oxidation. Then I have to use oxidizing agent that can undergo controlled manner of oxidation. So I will say controlled oxidation is carried out by a reagent which is known as PCC, which is known as pyridinium chlorochromate. Pyridinium chlorochromate. Pyridinium chlorochromate. It's a complex of your chromium trioxide, CrO3 होता है, उसके साथ pyridine, उसके साथ HCl. So it is forming a complex with all these three. It's known as pyridinium chlorochromate. So now let me see how we can do controlled oxidation. Suppose I have CH3, controlled as well as selective I will say. CH double bonded CH, single bonded CH2OH. This is 1 degree alcohol. When I give PCC, pyridinium chlorochromate, it undergoes controlled oxidation, and controlled oxidation means only this CH2OH will be affected and rest of the part will remain unaffected. So CH3CH, double bonded CH remains unaffected, and CH2OH becomes converted to CHO, aldehyde functional group. Now, 1 degree alcohol gives you aldehyde and acid. But if I take 2 degree alcohol, secondary alcohol, say R, CH, OH, R dash, and I give CrO3, which is an oxidizing agent, it will remove H and H minus H2, but it will give not aldehyde, but it will give ketone. Ketones are obtained. So 2 degree alcohol gives ketone on oxidation. 1 degree alcohol gives aldehyde, which can be oxidized to carboxylic acid. 1 degree alcohol can also undergo strong oxidation to carboxylic acid. And if you want to stop the reaction at aldehyde stage, you can give controlled oxidation reagent PCC and you can stop it. 2 degree alcohol gives ketone, but 3 degree alcohol do not undergo oxidation reaction. 3 degree alcohol will not undergo oxidation reaction. Now there is a reagent like copper. Copper reacts at 573 degrees Celsius differently with 1 degree, 2 degree and 3 degree alcohols. If I take 1 degree alcohol, this is your 1 degree alcohol. I treat it with copper 573 Kelvin. It will undergo oxidation and it forms RCHO. It gives you aldehyde. Suppose I take RCHOH R dash, and this is again my 2 degree alcohol, and I treat it with copper 573 Kelvin. It will again undergo oxidation and it will give you ketone RC double bonded O R dash. This is a ketone. You try to do the same thing with the 3 degree. Say I will not give actually R. I didn't want to give R because I need to give you the specific product. Suppose I take CH3, CH3 and a CH3OH. Now this carbon atom having OH is a 3 degree, so the alcohol is 3 degree, and I give you copper 573 Kelvin. So 3 degree alcohol will not undergo oxidation. Instead, it undergoes dehydration minus H2O. Alpha carbon removes OH, beta carbon gives out H, and there is a double bond between alpha and beta. So this changes the course of the reaction and gives you an alkene as the product of dehydration. Now, this is how 1 degree, 2 degree and 3 degree alcohol reacts with copper 573 Kelvin. Next, we'll discuss about something which is known as denatured alcohol. Denatured alcohol means ethanol contaminated with traces of methanol. MEOH means methanol. Ethanol contaminated with traces of methanol. At times, pyridine and copper sulfate is also added to it to make it unfit for consumption. ताकि ये consume ना हो जाए, unfit for consumption, because methanol may get oxidized if you drink it by mistake or maybe intentionally, whatever it is. the methanol gets oxidized to HCHO, methanol, and then it will again get oxidized inside your body to methanoic acid, which is harmful. Not in very less amount, but in excess amount it is harmful. It can cause blindness, it can cause death. So methanol gets oxidized to aldehyde methanol and also methanoic acid. So your body may get poisoned. So if a patient at all consumes denatured alcohol, what is to be done? As a treatment, intravenous infusions are being given, which actually contains diluted ethanol in order to damp the oxidation of this methanol to methanoic acid, because when you give excess of diluted ethanol, it actually damps the action of methanol and getting oxidized to methanoic acid. Now the enzyme that is responsible for the oxidation step of methanol to the acid becomes inactive, and your kidney can remove the methanol that you had consumed. So, denatured alcohol means the ethanol that is made unfit for consumption, that contains traces of methanol in it and may be mixed with pyridine that gives it a bad smell, copper sulfate that gives it a color, and actually you can understand that this alcohol is not to be consumed. If anyone consumes it, what happens is the methanol gets oxidized by the enzyme action to methanol and methanoic acid, which can cause blindness and can even cause death. So it's a threat to your body. How and what to be done if anyone consumes it? Intravenous infusions to be given of diluted ethanol in order to make the methanol or in order to actually stop the enzyme action, the oxidation of methanol to methanoic acid. Your body gets sufficient time to remove the methanol. So that's all for the session, because the session is quite long. So reactions of phenols will be done in the next session. Thank you all of you, and bye. So, after the entire discussion, are you able to answer the following questions like, out of alcohols and phenols, which is more acidic and why? If I compare carboxylic acid to phenols, which is more acidic and why? Can you prepare aspirin from phenol? Can you say what is the mechanism of dehydration of alcohols? Can you say what is the effect of acidity of phenols when there is an electron withdrawing group like a nitro group attached to it? Substituted phenols with electron withdrawing group, substituted phenols with electron donating group. How do they affect on the order of acidity? If you are capable of answering these types of questions, then yes, my video has achieved its learning outcome. Thank you all of you.